Hello everyone, let's continue to talk about optimization today. Today I want to talk about this example here. That's about maximizing a distance. Okay, so we often run into problems where we want to minimize the distance, but I want to do one that will maximize the distance and see how it's different. Okay, so let's look at this example here. We want to find a point or the points. Maybe there's more than one point on the ellipse. So that's an ellipse, right? As you can see, if you divide everything by 4, then you can turn it into the standard form for an ellipse equation. Then you can see that that will be x squared plus y squared over 4 equals 1. So that's an ellipse equation. That is, or are farthest away from the point 1, 0. And just know that when we plug the 1 into the x and when we plug the 0 into the y, it will satisfy the equation. So this point is actually on the ellipse. And so the shortest point, there is, it's actually really easy to find, right? It's actually the same point because the distance would be 0 in this case. But then we want to find the point that's farthest away from this point here that's also on the ellipse. And so how do we do that? First, we can try to graph the ellipse and see what the whole situation is. We're not doing any formal calculation at this point at the beginning because we actually want to see what the problem is talking about. Okay, so first thing is that we are going to start by just doing a rough sketch of the whole situation. So let's do that. Let's do that here. Okay, so what I'm going to do is that I'm going to just do a simple sketch of the ellipse. And you may say, how do we graph this one? Yeah, let me just look at this equation right here. So if we are looking at this equation, we have what? We have 4x squared plus y squared is equal to 4. So if we are dividing everything by 4, right? So let's do that. If you are dividing everything by 4, then we are going to run into the equation x squared plus y squared over 4. And that's equal to 1. So that's an ellipse equation. And then it's really just saying, okay, so the number under the x is actually just a 1, right? So you can write 1 under the x squared. And so we are going to get what we have, just 1 unit away from the origin, which is the center of the ellipse. And so we are going to put in the 1 in here. So that's just 1. And then the other one is also 1 unit away from the origin, so that's just 1 here, and then like the 1 here. And then because the number under the y square is 4, so in the y direction we have 2 units away from the origin, which is just 2 up and 2 down. So 1 2, so we get the 2 here, and then 1 2, and then we are going to get the 2 here. So see what's going on here. We can draw the ellipse. I'm not sure whether I should just use a line tool or simply just draw the ellipse like this. I think I can just draw it without using the line tool, because we are just doing a rough sketch and see what this whole situation is talking about. Okay, so that's that situation, right? Now, let's plot this point, which is 1 0. So if we plot the point on here, that's 1 0. That's right there. Okay, so this point, let me highlight that in green, and then you actually will get that point. So that's on there. Let me use a darker green color on there so that it's easier to see. Okay, now, so that's the point. Now our goal here is to find which point on the ellipse that is farthest away, or which points on the ellipse that are farthest away from this point 1 0. And then let's just think about this. We put a point here, then that distance is short. We move that point away from the 1 0 then on the ellipse, and then you can see that that will give you a farther away point, right? The question is, where is that point located, or where are those 2 points located? Actually, why do I say that there are 2 points? Because if you think about this, this point is actually just right in the middle of this arc right here. So what really happens is that if we are using symmetry, then if there is the farthest point that's above the x-axis, then there should be a point with the same distance from that point to this 1, 0 below the x-axis. So what that really means is that, let's say we pick a point, let's say right here, right? Let's say that's the farthest point away from the green point. And then by using the symmetry, we also have a point that's just having the same x value, but the y value would be opposite of the first point that we picked. And so the question is, are those two the points that we want? But then, of course, my graph is really just like just to see the idea, right? We actually have no idea where that point is located. Maybe it's higher or lower, depends on the situation. We have no idea. Okay, so to take a closer look at where those points are located, we can actually go on decimal and then check where they are. So let's go on decimal and see what's going on here. So now, let's plot the ellipse. The ellipse right here. Okay, so that's the same ellipse that we have, right? And then we also plot the given point, which is this 1, 0 here. So that's the green point. And then I'm not going to show the solution. Actually, I already found the solution ahead of time, and then I plot the solutions on there, but then I'm not going to show it right now. I just want to show what happens as we pick different points on there, and then what the distance is. And then we can probably see where that is located. Okay, so let's put down that point right here, and then you probably don't see what's going on here. I actually make a slider on here. So that's point C. There is actually a point D that will go below the x-axis and will travel clockwise on the ellipse. But then I'm just going to focus on the point C that will travel above the x-axis, and it's counterclockwise. And so see what's going on here. Once I move the slider, then this purple point will start moving. And then it will also show the distance between 1, 0, which is our given point, and the point C at the same time. So right now, because I'm setting my point C to be the same point as the 1, 0, so the distance between them would be 0. So that's the closest point, right? Point C is now the closest point, which is itself, which is just 1, 0 itself. Now, let's say if I start playing it, then the distance will start increasing, as you can see here. So see that if I start moving away from that point, then I'm going to get a straight line distance, which is, in this case, when the point is up here, then that's about 0.9, right? I can continue and see what's going on. So keep moving. Then you can see that the distance will just keep increasing, and it just keeps increasing until we get to the y-intercept. When we get to about the y-intercept, then our distance looks like it's still increasing, right? If you keep moving, then the distance is going to be longer, and it's about 2.23. Let's just keep going and see what's going on. It's still increasing, 2.3 now. And then it feels like the distance starts dropping after we get past some point here. We don't know what that point is, but after we pass a certain point, and then you can see that the distance drops back down to 2.27. It was 2.3 at some point, right? And if you just keep going, then you can see that the distance will just keep dropping. And then when we get down to all the way down to the bottom right here, as you can see, the distance will be 2. We don't even need to use the distance formula to find the distance between those 2 points. You can just count, right? That's 1, that's 2. So distance will be 2 in this case. So now, if you travel on the other direction here, if you look at the D here, then you can see that, let me just show you. As you can see here, if we are using symmetry to find the distance between point D and 1, 0, we can actually just see that, okay, so the distance between point D and 1, 0, it's really just the same distance between point C and 1, 0. Yeah, so that's why we don't need to worry about the point D here. Of course, we may still need to find this point D, but once we find point C, point D is easy to find. So the question is, where is that point? We know that it's about like 2.3. That will give you the maximum distance. The maximum distance is probably just 2.3 something. Do we know the exact value? We actually have no idea by just moving the slider here, but then we know that it's around this area right here. So the next step is to actually use calculus to find this exact location that we want. Okay, so let's go back to the problem, and then we want to start solving the problem. Okay, so how do we do this problem? First, because we are talking about the distance, right? We are talking about the distance between 2 points. So first, we need to review with ourselves the distance formula. So let me write it down here. So let's recall. Let's recall something here, the distance between 2 points. Let's say we have x1, y1, and x2, y2 is given by the formula, right? So you remember the formula, it's the difference of the x values, square that, and then we are adding that to the difference of the square of the difference of the y values. And then we are going to take the square root of that quantity we are getting. So that's the distance. And then, so we are trying to maximize this distance here. To maximize the distance, that means we need to take the derivative of this function. And to take the derivative of this function, it may seem that it will be easier if we can take the derivative without dealing with the square root. And in fact, we can avoid dealing with the square root by maximizing, instead of the distance, we can maximize the square of the distance. Okay, so if we maximize the square of the distance, and we can also at the same time maximize the original distance between those 2 points. So let's do that. Okay, so what we are going to do is that we can start the problem by saying, okay, so if we try to maximize, we can try maximizing, okay, the square of the distance between the green point and the purple point. And of course, the purple point at this point is just unknown, right? The distance between what? Now, there are 2 points that we need to worry about. One of them is the green point, which is 1, 0. And the other point is the purple point. And because purple point is unknown, then we got to use just xy to denote that purple point. Is that good so far? Okay, so what do we do? Let's put down the distance function, okay? So what do we have here? We are going to, let's just call this the square, the distance, call this function f. So we can call this the square of the distance. We call this the function f. Actually, you can call it something else, right? It's up to you. It doesn't really matter. This is really just a name, right? So we can call that f of x. Okay, and that's equal to what? That's equal to, now because we want the square of the distance, so that means we're squaring the square root, so we don't need to worry about the square root anymore. We only need to worry about the stuff that's on the inside. So we are going to have what? We are going to be having now the difference between the two x values. So usually I will put the unknown first. So that will be the x value right here. And then minus the x value for the green point, which is just the 1, because we're finding the distance between the 2 points, right? So I put the 1 right here. And then square. And then plus. Now the difference between the y values. So we have the y value there. Okay. And then minus. Now what about the y value for the green point is 0. So we have the 0 there. And then we get a square. But then, as you can see right here, we are writing f as a function of x. But there is a y in here. So how do we got to do something, right? But we also know that y is a function of x. How do we know that y is a function of x? Because we are saying that this purple point, it's a point that lies on the ellipse. And so instead of writing y, we can actually use the ellipse equation and then help us find an expression in terms of x. And so let's do something here first. Let's do something here. So what can we do? We can do this. So we have what? We actually have, from the ellipse equation, we have 4x squared plus y squared, and that's equal to 4, right? And how do we solve for y here? We can actually solve for y by isolating y. So we are going to get y squared is equal to 4 minus 4x squared. Okay. And then if you want, you can take the square root, but it will tell you just plan a little bit ahead. And then you can see that if we do y minus 0, then what happens? We get y. And then we are going to square it, so we can actually just replace the whole y square using this 4 minus 4x squared. But it's up to you. It doesn't really matter. Eventually, you are going to still get rid of the square root, right? It makes no difference. So let's continue with the problem here. And so our function, right, f of x is equal to, okay, so continue with that, the x minus 1, right? And then plus. Now, as I said, y minus 0 is y squared gives you this 4 minus 4x squared. So we can just put that 4 minus 4x squared right here. 4 minus 4x squared. Okay, so this is the function that we are maximizing. Okay, so how do we maximize a function? First thing, we need to take the derivative. Okay, so let's take the derivative and then find the critical numbers. So the idea is that, okay, so find the critical numbers. What do? We need to take the derivative. So f prime of x is equal to, it's up to you whether you want to expand this x minus 1 square. We can simply just take the derivative directly. So we are going to get 2 times x minus 1 using the general power rule. And then plus, now the 4 will disappear, and then this negative 4 x squared will become, right? So it shouldn't be plus anymore. It should be minus ax. And so we are getting a really simple derivative. And we can try to simplify this. So it becomes 2x minus 2 minus ax. And so that becomes what? Negative 6x. Okay. And then minus 2. So that's simple, right? And then now, because we're finding critical numbers, so first case is that f prime, we set it equal to 0 and then try to see whether that will yield a critical number for us. So we get negative 6x minus 2 is equal to 0. And then, of course, that will yield a critical number, which is x equals negative 1 over 3. And then because we're actually getting a linear function right here, right? That's our first derivative. Because that's a linear function, there is no value that we plug in that f prime for which f prime does not exist. So that's really saying that, okay, so there is no x value that will cause the f prime to be undefined. Okay, so there is only one critical number. Now, what do? We can, next step is to show that it's a local maximum. If it's a local minimum, that's not helping us, right? Because we actually want a local maximum in this case. So let's see what's going on here. We have, let's do the sign analysis chart here. Okay, let me draw that again. This is our sign analysis chart. This is the x-axis, and then we put that critical number on there. That's the only number that we are going to be putting on here. And then we can just pick some number here. But remember the domain for the x. I mean, for the domain for the function, I actually forgot to mention that. Just put a note on the side right here because that's also important to remember. Here's the note that's important. The domain for the function is actually what? The domain for the function is actually, if you just go back to our sketch right here, do you see what's going on here? Because we're really just finding the points that are on the ellipse. So if we're using x as the independent variable, we really just need to make sure that, okay, so the point lies on the ellipse. And so that means we cannot really have any other x values that's greater than 1 or any x values that are less than negative 1, right? So the domain is actually really just negative 1 to 1 for the function. And because the function is continuous on this interval, we actually don't even need to do the sign analysis chart. All we need to do is to plug in the critical number, plug in the two endpoints into the function, and then we can find the absolute maximum. But I'm still just showing you that, okay, so we can also apply the theorem that we talked about, the first derivative test for absolute extreme values, where it says that if there is only one critical number, then, and if the function is continuous on the domain, then what happens? Then we can say that local extremum is also an absolute extremum. Yes. So both ways will work. Will give you the same answer. Okay, so let's just pick some number here. We need to pick something that's in the domain, right? So let's just pick that. And simply just pick 0 on there, right? Picking 0. 0 is in the domain. So we pick 0 and then plug it back into our first derivative. So we get negative 6x minus 2. Plug the 0 in there, we get negative. So that's a negative number, right? And so now we can say that the function is what? It's decreasing. And then on this side, what can we pick on there? We can actually just pick negative 1, right? And then if you put negative 1 in here, that becomes 6. 6 minus 2 is positive. So the function is increasing before negative 1 over 3. So do you see what's going on here? The function is increasing before negative 1 over 3, and then it turns into decreasing after negative 1 over 3. So you can really see that the function is increasing, going up, and then it goes down. So that tells you that's a local maximum. Okay, so now we can actually start drawing the conclusion. We can say that since f is continuous on the domain negative 1 to 1, and x equals negative 1 over 3 is the only critical number in this interval, right? Then we say that f has an absolute maximum at x equals, what is that? That's negative 1 over 3. Yeah, so we show that that's will give you the maximum. Now, we just need to find the maximum value by, what can we do? We can plug it back into, because we want to find the point, right? We want to find the point, and we may also want to find the maximum distance in this case. So depending on the situation here, you can plug it back into the distance formula to find the maximum distance. But if we are just finding the point, then what happens? Then we can actually just plug it back into this y squared equals 4 minus x squared to find the y value. So let's do that. And if we are just finding that y squared is equal to 4 minus 4 times something square, what is that something? That's negative 1 over 3, right? We plug it back in and then do the calculation. I'm going to skip the calculation right now because that's really just basic calculation, right? So we do all that calculation, we are going to get 32 over 9. And so that tells us that y is equal to plus or minus 4 times the square root of 3. And so finally, we say that the points, actually there are 2 points. Why are there 2 points? Because one that's above the x-axis, the other one is below the x-axis, because when we square root both sides of this equation, we are going to get plus or minus. So the points that are farthest away from the green point 1, 0, right, are the 2 points, the 2 purple points right here, negative 1 over 3. That's the x value that comes from the critical number. And then the y value would be just one of them is the 4 square root of 2 over 3. And then the other one has the same x value, but a different y value. And so those are the 2 points. Now this problem is finished. Those are the 2 farthest points away from this 1, 0. And then now let's actually go back to the decimal animation that we had before and see what actually is going on. Are our answers accurate, or are they correct? Let's find out. So let's move them back into the green point here. What's going on here is that I'm going to show the solution. So those are the 2 points that we have here. Now, let's see that those are the 2 points that we found, right? If we look at the solution, I actually typed them in. So as you can see, the 2x values are the same. The y values are opposite of each other. 4 times square root of 2 over 3. And then what are we doing here? Let's see what's going on. So we start moving the purple point. And then when it hits those two locations right there, then we are going to get the maximum distance. And the distance would be 2.3 something. Yes, you see that it's almost there, so slightly larger. And then once we go past those 2 points, the distances will start dropping again. Okay, so you can see that it's going to be shorter than the distances for compared to those two red dots on there. Okay, so this problem is finished. Hope you enjoyed this video, and if you find this video helpful, please subscribe my channel and then give me some support. I will continue to make more math videos. Thank you for watching. I will see you next time.